4.5, number 39, we're asking specifically about the asymptotes piece. Hello. Thank you. Anise.
So, first, there's no horizontal asymptotes. You don't need to determine that. Like, that's this. I know this to be true.
That's fine.
But for vertical asymptotes, I don't really understand how to write it, I guess.
So I'm going to set the denominator equal to 0.
Okay.
Cosine x is equal to -1 at just one place on the unit circle. That's pi. And then I'll get another asymptote at every spot coterminal to that, which would be adding any whole number multiple of 2 pi. So that's the way I would write my asymptote, as I'd write it that way.
So I wrote it.
Okay.
On the right track, I guess.
And since this is a periodic function, whose period is 2 pi, if I'm graphing just one period of it, I just have just one asymptote in the period that we're going to be graphing. You know what I mean?
But there's no but it doesn't specify in the question that it's from
No.
0 to 2 pi.
But if I'm graphing a periodic function, am I graphing it infinitely? Well, no, I'm just going to kind of graph one period of it.
You're right.
And then just kind of go about my business, right? So that's when I'm actually going about graphing the thing, I would just graph one period where I really only the one asymptote I care about at pi.
Okay.
Is that okay?
Yep, I get what you're saying.
Okay. Did you have more on 39, or was that just kind of...
I just don't, okay, and then I don't understand, because the way that I did it was I tried to evaluate the limit of period.
The limit of the period?
Yes. But I guess I don't think I need to do that.
Well, I mean, you'd say the limit as x approaches pi of sine x over 1 plus cosine x is going to be 1 over 1 plus the limit as x approaches pi of cosine x. It's like -1. Right, if you want to use a limit to do it, that's okay.
Yeah, that's okay.
I used algebra to kind of figure out where I'm looking for my asymptote at, and I can use a limit to verify that. And I know it's going to be
So all I really needed to do was just say, because I totally get the pi plus the 2 pi k, where pi is 1 per period. It's 1 per period. So then
I should probably write this. I don't know that
is that just do I need to verify it with a limit? Because I got really confused when I got to the limit part. Don't really get what I was doing.
No, I don't think so.
Okay. Cool.
I mean, denominator equal to 0 gives you vertical asymptote, right?
Yeah.
We get that.
Yeah.
If you wanted to verify it afterwards, fine. If you didn't, fine. I don't know that it's that big of a deal. If the net result is just trying to get a graph out of the thing. Does that feel okay?
That makes a lot of sense, yep.
Okay.
It's a lot of pain and suffering for nothing.
Well, hopefully it's productive pain and suffering, though.
It was.
You thought deeply about what was happening, and that's often helpful, even if you don't make any actual progress with whatever it was.
Yeah. Yeah.
So, others with questions on stuff. Okay. If you guys change your mind, we can always come back and do some more. Today we're going to be talking about 4-7. We are skipping 4-6. 4-6 is just like 4-5 again, which it feels like once is enough. 4-7 is optimization problems. And I would say that in general, this is most similar to the related rates problem that we've done before. So it's very much the setup is the hard part and the calculus is kind of easy. So that's going to be kind of the gist of it. So the textbook has some steps for solving these optimization problems. Step number 1 is to understand the problem. First step, to read the problem carefully until it is clearly understood. That means if you don't understand what it's going on, keep reading it and thinking about it till you do. Helpful questions you might ask yourself: what is unknown? What are the given quantities? What are the given conditions? Step 2 would be to draw a diagram. In most cases, these are going to be like kind of a geometric-ish questions where there's going to be, you can draw a curve, or you can draw a shape, or you can draw something to kind of help you keep track of the quantities and the relationships involved. Step 3 would be to introduce notation. So first, we would assign a symbol to the quantity that's being maximized or minimized. For their purposes, they're going to call that Q. And then symbols like A, B, C, D, etc. for the other unknown quantities. And then label the diagram with these quantities. In the no doi tip of the day, it says it may help to use suggestive symbols. For example, A for area or H for height. Yeah, I know, right? And yeah, I just, at that point I was like, I'm done reading this. It's like, yeah, this is the no doi of the century here. Step 4 would be then to write an equation for Q in terms of your symbols in step 3. Step 5 says if Q has been expressed as a function of more than one variable, use the given information to find relationships among these variables, then use these equations to eliminate all but one of the variables for the expression of Q. Thus, Q will be expressed as a function of one variable, say x. So you have Q is going to equal some f of x. Then we'll write the domain for that function. And then the last step would be to use the methods from sections 4.1 and 4.3 to find the absolute maximum or minimum for f. In particular, if the domain of f is a closed interval, then we have to use that closed interval method in from section 4.1. Okie dokie. All right. The rest of this is basically examples. So no new concept, no new ideas going on, just going to be all application here. So we're going to take these things we already kind of know about and solve some problems here. So a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Everybody feel pretty decent about what's going on? I don't think this is particularly confusing. So draw a little picture here. So here's my river. And then we'll draw our rectangular fence. Everybody feels good about that? Okay. What quantity is being maximized or minimized?
Area.
Area of the field. Great. And are we maximizing or minimizing? Yeah. So we're going to maximize the area. And the shape of this field is rectangular. So the area is going to be, or length times width, or whatever you want to name it. I'm going to call it length and width. Okay? Base and height is fine. I'm using L's and W's. That's what I like. So let's go ahead and label our picture then. Everybody's okay there? So what's the problem with the area formula that I've written here? It's two in terms of two variables. So I need to find a way to either eliminate or rewrite W in terms of L or L in terms of W. It doesn't really matter which. What am I going to use to do that? What piece of given information haven't I done anything with?
2,400 feet.
What can I say about the relationship between L and W in that 2,400?
2W.
Yeah, L plus or W plus L plus W is equal to 2,400. Or that L is going to equal 2,400 minus 2W. So I can say then my area formula now in terms of W, so I'll write it as A of W, is going to be 2,400 minus 2W times W. Okay? Everybody happy with what we've done so far? We need to determine a domain now for this function. So what values of W are acceptable inputs? What's the lower bound on that value for W? Zero, right? W is a width. Widths can't be negative, surely. So 0 seems like a good value there.
Would there be no equal to?
Well, a 0W just would mean like no field. So I think it's still okay. I think it's still okay. And to be frank with you, like having this bounded is better than unbounded. Is there an upper bound for W?
Well,
1,200, excellent. Why?
because L could be 0. Then you would just have 2,400 divided by 2.
Okay, there's a better reason for that though then. What happens if W is bigger than 1,200 there? You get a negative. Can area be negative? No. So that's, I would say, is a better reasoning than what you had stated, Tegan, although you had the right value. Okay, everybody happy? All right, let's do our calculus now. Before I do my calculus, though, I'm going to do a little bit of simplification so I can avoid having to do like a product rule. Because, like, why wouldn't I just distribute to make my life easier there? So there's my derivative. So let's investigate the critical values now. Is there any place where that derivative is undefined? No, because it's a polynomial. So all I need to worry about is when it's going to be equal to 0. So I'm going to subtract over the 2,400 and then divide by -4. So there's that. Now, using my method from 4.1 in finding the absolute maxes and mins on a closed interval, what values do I need to evaluate? 0, 1,200, and 600. Good. The nice part is clearly a of, well, I don't know why I wrote f's here. Right? What's our function name? A for area, yeah. Okay. If I plug in 0 for a, what do I get? Zero, right? Not into a prime, but into a. If I plug 1200 in for a, what do I get? Zero. Okay. And if I plug 600 in, I get 7,200 or 720,000. So which one of those constitutes the maximum? A of 600. So the question's asking, though, for the dimensions. So we know that W is 600 feet. How do I find the length? Yeah, exactly right. There, we're done. That wasn't so bad. Pretty straightforward, right?
Couldn't we just set logic? Like, I mean, like, obviously this is calc, but like, couldn't we just say, oh, because like it's a because a rectangle, like a square is a rectangle, and a square must have like the largest area. Like, can't we just say that, oh, therefore it's like 1200 by it would be a 1200 by 1200 space.
Sure. But what happens if the river looked like that? And you're building like something like this.
But then that's not a rectangle.
Right, exactly.
That's true. Yeah,
right?
You're right on that.
So it's like this method scales really nicely. Sure. You're right.
But that's like a super specific.
But this is, yes, it's specific to this instance where it's like I can build, the shape I'm building is like a rectangle missing a side. All right. Next question. A cylindrical can is to be made to hold 1 liter of oil. Find the dimension that will minimize the cost of the metal to manufacture the can. Everybody have a good picture in their mind of what we're doing? Okay, what are we trying to maximize or minimize? Okay, how much metal we need to manufacture the can? Sure. Geometrically, what is that?
Trying to minimize base height. Or radius of height.
Yeah, the surface area. That's really what we're trying to minimize. How do we calculate the surface area of a cylinder? We have the area of the top and the area of the bottom. Everybody agree with that? Plus, and then you have the area of the sides, right? What shape is that side if you unfold it? A rectangle. Great. What's the base of the rectangle? The circumference of your circle. Excellent. So that would be 2 pi r. And then the height of your rectangle is your height for your cylinder. So that's our surface area. Okay, everybody happy with what we've done there? What's the matter with this surface area formula we've written? Two variables in it. Okay, so we got to either rewrite this in terms of R or in terms of H. Which one do you suppose I would prefer? I'd rather write it in terms of R because I only have one variable to replace rather than two. Yeah, find it. I think you meant what you just didn't say what you meant. Yeah, because it was kind of an awkwardly worded question. Great. What am I going to use to do that? Algebra. Great. So insightful. I think somebody said math last hour when I asked them the similar question. It's like they're thinking hard this morning. What piece of given information haven't we used yet? Okay. The 1 liter is representing what kind of quantity? Volume. So the volume of a cylinder is area of the base times the height. Now, 1 liter I'm going to rewrite using like linear units. My chemistry students, what is 1 liter the same as?
1,000 moles. I'm sorry.
No, that's okay. And what is one milliliter equal to?
1.
It's 1 cubic
Oh shoot.
centimeter. Think about like a cubic centimeter. It's just like a little tiny cube like this size, right? What's going to fit in there? Like 1 milliliter of liquid.
Okay.
So 1 liter is 1,000 cubic centimeters. And I want this because I need my unit at the end to be a linear unit, right? Having 1 liter in there isn't super helpful to me because at the end of the day, I want my radius and volume, or my radius and height, which it's asking for the dimensions, need to be in some kind of like distance unit. Squared. Everybody's cool with that? So now if I drop this in here for surface area, I have that.
So like the essay in parentheses R, that just means like surface area in relation to R.
Yeah, now it's a function of R. Yep. So I'm just kind of really pounding away at the notation there to make it super clear. Let's go ahead and do some reducing here, right? Or simplifying. So I'll write it that way. You could write it over R also. Domain, what can we say about R?
R has to have a minimum of at least 0.
Well, R can't be 0 because it would make the derivative undefined.
Well, yeah.
Or make the function undefined. So we know at least R has to be greater than 0, right? Can't actually equal 0 because if it did, SA would be undefined. Okay. Is there a maximum value of R? Well, if you make R to be 1,000, I can make the right size cylinder just by picking a much smaller h, right? H might just have to be less than 1, but that's okay. So it's really unbounded. right? R can be as big as you need it to be. H will just be real small.
Oh.
So you'll end up with like a puddle, something that's like, 100 meters wide and like 1,000th of a meter or 1,000th of a centimeter thick or something. It'd be dumb, but like you could do it. You know what I mean? Yeah, like remember the oil slick related rates question? Same kind of idea. So this is unbounded. So what does that tell us? We're going to be using like our 4.3 ideas here. Okay. All right. So let's do our derivative. And notice that with the way that I wrote this, it's a really easy derivative to do. So first thing we'll do is looking for critical values. Are there any values of R where this derivative is undefined? 0. But is that a problem? Is that actually a critical value? No, because it was also undefined in the original function, right? So you can't be a critical value if you're not in the domain of f, right? So we don't have to worry about that. So all we have to worry about then is where the derivative is equal to 0. Okay, algebraically, what's going to be the best thing to do to start solving this for R? Well, it's not really, one's a negative exponent, so it's like you can, but it's weird. Multiply both sides by something. Yeah, R squared. Let's see what happens when I do that. Not only do I get rid of the negative exponent and the fraction involved, I actually get all the r's into one place in addition, which is pretty rad. So to get this by itself, we're going to add the 2,000 over, divide by the 4 pi, and then we'll cube root both sides. Now I could reduce this a little bit, right? So maybe we, let's actually, let's do it this way. So we got here the cube root of 500 over pi centimeters. So that's my value for R. That's my only critical value. How do I know that's a minimum?
Because maximum, because as you said, there's an increase, there's an endless bound, like an endless upper bound, and think about it, as you make a bigger radius, a smaller height, you're just going to be, you're not going to be decreasing surface area, you're going to be increasing.
It's a very nice geometric argument. Is there a calculus argument that we can make? Well, here's what you could do, right? You can do a test value, right? Like you pick an essay that comes before that and after that and show that we go from decreasing to increasing. Or what I would prefer is do a second derivative test. So the second derivative is 12 pi r squared. That is something that's always going to be positive, right? So we know that if the first derivative is 0 and the second derivative is positive, the second derivative says this is going to be a minimum. A minimum. Is that okay?
Wait, why would you?
I just took this thing and differentiated it, right? That's still the same thing as that's still our first derivative.
But isn't it like your first derivative multiplied by r squared? Which you can't really do because it's equal to 0. Like, you can do whatever you want because it's equal to 0 now, but like, wouldn't you also have to do the same thing to the double prime or to the second derivative then?
Hold on one second. Sure. Let's try it again. So that's going to be 4 pi plus 4,000 r to the third, negative third, right? R has to be positive.
Yep.
So all positive.
Okay.
Fair.
Got
So it was a fair criticism.
Okay.
You're right.
Yeah, I get what you're saying.
You're right.
Okay.
The outcome's still the same.
Uh-huh.
We have something that's always positive.
Yeah.
So we know that this is a minimum. Everybody's happy now? Okay, what do we still need? H. Very good. How do I find H? So we'll just plug in our value for R. Let's see, let's do some no calculator simplifying. Obviously, you could plug this into your calculator at this point. Really, lots of points earlier than this even. Oh, yuckers. I should have kept that. Well, it's fine. I'm not messing around with it anymore. Whatever. What's Mr. Kulik regretting? I'm regretting simplifying that to 500 instead of leaving it as 1,000 over 2 pi. Because when I do the cube root of 1,000, I could do something with that.
Oh.
Now I'm stuck. But it's fine. It's whatever. All right. Anyways, you type that in your calculator, you get some number out of it. I don't care what the number is. Nor should you. It's just some stupid number. Oh, but they're in centimeters. I should say that. Okay. Everybody happy-ish? All right. So again, this is just summarizing some nonsense that we'd seen before. Let's do another example. Find the point on the parabola at y squared equals 2x that is closest to the point 1, 4. Okay? Now, 1, 2, 3. So let's I'll just call this the point A or something. All right. How do I graph this parabola y squared equals 2x? I'm just going to pick values for x and then plug in the corresponding values for y, right? What value of x do you suppose I'd want to start with?
1.
I mean, I'd do 0. It's okay. So plugging 0 in for x, y has to be 0, right? Okay. Plug 1 in for x, what does y have to be? Close. Plus or minus the square root of 2. Again, it's a parabola, so it should be looking like a U shape. If y is 2, if x is 2, what does y have to be? Plus or minus 2. And so we're going to have something that looks like this, right? Everybody agree? So we're looking for whatever this point P, where that distance is minimized. Excellent. Okay. All right. How do I calculate that distance between those 2 points? So if you didn't remember, shame on you, but that's an expectation that you'd remember that. Nobody's going to give you the distance formula again. That's something you've seen since Algebra 1. The expectation is that that's still in there somewhere rattling around next to, reruns of Family Guy or something. All right. So let's say that AP, so we'll make P our x2 and x1. We'll make A our x1 and y1. Does it really matter which one I put first or second? Yeah, not as long as you keep them paired together, right? Everybody's good with this? All right. What's the problem, though? 2 different variables. Oh, no. So you either need to rewrite x in terms of y or y in terms of x. Which one do you want to do? I'm going to write x in terms of y. Because, willy-nilly, that's easier than having to worry about the plus or minus in there, right? Actually, let's save myself some space. I guess I could write this d of y now, I suppose. All right. What do you suppose Mr. Kulik's going to do next? I'm going to do something before that to make this taking the derivative easier, because this looks like a pretty crappy derivative to have to take. I mean, you could do that. I'm going to skip doing that also. I'm going to make a different argument. Okay? So the distance is always a positive quantity, correct? So where the distance is minimized would be the same place that d squared would be minimized. Everybody agree with that? So if I do that, it'll still give me the same value if I worry about d squared. But what did I just get rid of? A chain rule, right? And a pretty nasty one at that, right? Now I'm happy to differentiate because these little chain rules I feel pretty good about doing. I don't see myself messing those up. And if I simplify this down, what do I got to get? Y cubed minus 2y plus 2y minus 8. Or just y cubed minus 8. Oh my goodness, we forgot to do something. What did we forget? Yeah, the domain up here. What are the feasible y's that I could plug into this function?
All real numbers, because even if you have 0, it's squared, so even if there's negatives, you're still going to get a positive answer, and it has to be positive.
Absolutely. Yeah, it should be all real numbers. And even you could look at the picture and come up with that, right? Like, what are the feasible y coordinates here? All real numbers, right? Any y is possible on that function, so should be good, all real numbers. All right. So if I look at the derivative, is that undefined anywhere? No. So the critical values are just going to be where that derivative is equal to 0. So that's going to be 2. Wait a second, Mr. Kulik. It's a third-degree polynomial. You only reported one answer. Aren't there 2 other answers? Yeah, there are. What are they? They're imaginary. How can Mr. Kulik look at that on site and tell that the 2 solutions, or the 2 other solutions, that cubic polynomial, are imaginary without doing any work? It's a great question, isn't it?
Right.
That is a difference of 2 squares, or 2 cubes. The sum or difference of 2 cubes always have 1 real solution and 2 imaginary solutions. Done. Yep. If you remember the factoring pattern for the difference or sum or difference of 2 cubes, is this, right? That piece will always be imaginary.
Is that an input plus or minus?
Yep, because it's the opposite of whatever the other symbol was. All right, so there's my value for y. How do I know that's going to represent the minimum?
Because the only other solutions are imaginary.
Well, couldn't it be a maximum? So what I would do to check this is either plug in two values on a value on either side of it into the derivative and show that we have decreasing to increasing, or you could look at the second derivative. I do the second derivative in this case because it's super easy to get. It's just going to be the derivative of y cubed minus 8. And I note that that's always positive. So this is a minimum. Everybody's cool with that? Now I need the coordinate here. I have only the y coordinate. Where am I going to get the x from? Right there. So we're just talking about the 0.22 for all you ballerinas out there. Yeah, that was a good one. I heard snickers. Like, I can't believe I'm about to laugh at this, but I'm going to do it because he snuck it in there. All right. Doing okay? Again, the calculus pieces, not bad, right? The setup is the difficult part. All right. Example 4. A man launches his boat from point A on a bank of a straight river 3 kilometers wide and wants to reach point B 8 kilometers downstream on the opposite bank as quickly as possible. He could row his boat directly across the river to point C and then run to B, or he could row directly to B, or he could row to some other point D between C and B and then run to B. If he can row 6 kilometers per hour and run 8 kilometers per hour, where should he land to reach B as soon as possible? We assume the speed of the water is negligible compared to the speed at which the man rows, i.e. it's the water is still, right? That there's no current working against him to slow him down. Do you guys understand what's going on here? So we have some river, right? We're starting at some point A and wanting to get to some point B. And the question is, do I do like this and then this? Do I do this, which is the least distance, but I move the slowest in water? Or do I do like some combination of it? Or I do like that?
C, is that?
Nothing special about point C. It's not supposed to be like halfway or anything like that.
D is between D and C.
Oh, there. I'm
I thought
sorry.
C was
Oh,
the
yeah.
triangle.
All right. Yeah. Yeah, the question said that was C. And then it said that this was going to be D. Whatever. Okay. So rather than using my chicken scribbles, here's the nice picture that the book generated. But it's the same picture, right? It just doesn't look like a bunch of scribble scrabbles. All right, everybody happy with the picture we've drawn and the labels we've given? What are we trying to minimize again? Time, yeah. How is time calculated? In our case, it'll just be the distance traveled divided by the rate at which you're traveling, right? How long does it take to go 100 miles if you're going 50 miles per hour? 2 hours. 100 divided by 50, the distance divided by the rate. Everybody's happy with that? Okay. So what do we got here then? So what is that? What is the distance then that we need to travel in this case? We need to go AD plus DB. Or that point D can vary between C and B. Everybody agree with that?
So I get asked for 3 possible options. Then
No. It says, well, the third option is infinitely many.
right. I could propose a D spot, but what if like going to C and running or just going to B is fast?
Well, D is going to vary between C and B.
So it could
Right,
be C and
where-
B.
Yeah,
Okay.
that's what we're kind of saying. Where D is going to be some point along that bank between and including C and B. So yes, that's going to include row straight over and then run the whole way, or just row straight to the point and do no running, or some option in the middle. Everybody's okay with that?
So you're just kind of including the possible other scenarios in that.
Yes. Yeah. And then anything in between, where you row some other intermediate spot and then you do some running. Okay. So that distance AD is going to be right, and AC is, yeah. So AD is just going to be x squared plus 9, or the square root of x squared plus 9. Everybody happy with that? What's DB going to be? Excellent. Okay. What's the rate that we're traveling on the segment AD? So we can row at 6 kilometers per hour. And the rate for the running piece was 8 kilometers per hour. So my t of x function is going to be that. Everybody agree with that? Okay, what's the domain for x going to be? Or the domain for t of x, I should say. What are the acceptable values for x? Well, what happens if d is equal to c? X would be 0. And what would happen if d was equal to b? X would equal 8. So that's going to be my domain, right? 0 to 8. You guys happy with that? Okay. So go ahead and do my derivative. Well, let's do this first. What's up? What can't you read? x squared plus 9. Yep, all under a square root. So I'm going to write it like that before I take my derivative. Is everybody okay with that? Can we see why I'm doing it that way? Just makes the calculus a little bit simpler. All right. Oops. Come on. Oh, that was too far up. So t prime of x is going to be 1/2 times that 1/6 x squared plus 9 to the negative 1/2 now times 2x minus 1/8 plus 0. Everybody's cool with that? I think it's actually, it should be written this way, 0 minus 1/8. Okay. Any place where this can be undefined? There. We'll write it this way for you so it'll be easier to see. How about that? That probably makes it a little bit easier to see. Is that undefined any place? No, right? The denominator can't ever equal 0 because x squared can't equal negative 9. And x squared plus 9 always has to be positive, so that can't ever be undefined. So this is the only places we're worried about is when the derivative is equal to 0. Oh, the 6 should still be there, but the 2's canceled.
Yeah.
Sorry, the 6 should still be there. Yep. All right. Algebra time. How do you want to solve that?
You would only care about the numerator, so wouldn't you just have to...
Well, if I only care about the numerator, I'd have to make a common denominator and add the fractions. Here's what I would do. So I'd add the 1/8 over. And then I'm going to multiply both sides by 48 x squared plus 9. Why 48? Actually, I shouldn't do that. I should do 24, right? That's the least common. 48 would have been okay, but I would have just had reducing left to do. So I'd end up with 6 square root of x squared plus 9 over here equals 4x over here. And that shouldn't be 6. That's a 3. Dum-dum. Okay. I'll divide both sides. Maybe I'll just square both sides first and deal with that. Maybe that's better. Less fractions. I don't know why I got x. Oh yeah, x is fine. Plus or minus 81 over 7 under a square root. Everybody's okay with that? And that's really, don't care about the negative. Why not? It's outside of the domain of x, right? X was 0 to 8. And then this is kilometers, I think. Okay, what do I still need to check, though? I need to make sure that that is indeed the minimum, right? What's going to be the best way to do that? I could do the second derivative, or I could plug in a value on either side of this into the first derivative. That's okay too. Again, if you have a calculator, that's a perfectly reasonable option that's pretty fast. If you didn't, the second derivative test is probably a little bit easier. So what do we get there? We're going to have negative 1/2 x squared plus 9 to the negative 3 over 2. Oops, and I still have that 1/6 floating around there. And then times 2x. And I notice that this has to be Oh, what am I doing here, Mr. Kulik? Quit being dumb. We shouldn't do that. Why shouldn't we do that? Why shouldn't we do that? The domain is closed. It's closed, right? So I just need to do t of 0, t of 8, and then t of 9 over square root 7. So if I plug 0 in for t, I get 3 over 6 plus 8 over 8, so 1.5. If I plug 8 in, I get 64, so square root of 73 over 6 plus 0. Square root of 73 plus 6. Okay, it says 142 is what about that is. And then the other one, if I plug in 9, oh boise.
Is that 1.42 or 142?
1 point. So those are hours again, remember?
Oh, yeah.
And then if I plug the last one in, I get 133. So this is my minimum. So you want to hear a funny anecdote? It's not really an anecdote, but like a funny observation. So like people have done this same kind of thing with a dog on a beach, where like you start here and you throw the toy out into the water, and the dog like inherently like knows without doing anything like how far to run along the beach before going into the water to get the toy to get it to it fastest. They do like a really great job of approximating the solution to this somehow. Isn't that weird? Yeah.
That's nuts.
That's nuts, right? Like the dog inherently just knows instinctually, apparently, the fastest way to do that. I don't know how the animal's doing that, but like for some reason animals are often really good at these really difficult optimization problems. And somehow like they have a heuristic hardwired into their animal brain that takes care of it. And I can't do any calculus, but they somehow come up with a pretty good answer.
Is there an observed pattern in like math that has to do with this kind of thing? Like, have we figured out like because the dogs aren't using calculus, like no way.
Yeah.
So then, like, is there like a pattern?
Well,
in, like,
the
these kind
pattern's
of
gonna
situations?
change based on like how fast you can run and swim,
Does the dog does not?
and like how far away the thing is from land. You know, like all that stuff matters to like the, you know what I mean? Like I don't know how the dog's doing it. It's a really bizarre. It's like a really bizarre phenomenon that animals in general are really excellent at this kind of thing. Like if you look at, you know, like a bee is in like a flower garden or whatever.
Yeah, I've seen this before, and it's like they made the hives like different parts of a city.
Well, like let's say that this is where the beehive is. The bee's gonna like instinctually know the fastest path to visit all the flowers and go back to the hive.
Yeah.
Which is a really difficult like computational problem to find like the shortest path through something like that.
Yeah.
Especially the more things there are. And like somehow the bee always almost always picks a really good solution, if not the best, if not the shortest path, something really, really close to the shortest path.
Yeah, I was reading about this, and it's like so it's like they've taken city like bus line or like city underground lines, and they've set it up for a beehive for like in a bee enclosure, and they found that the actual way that the bees do it is more optimized than the way that civil engineers set it up. Mm-hmm. Which is like that's crazy.
Or even like watch like, you know, like swarm traffic. Like if you have a bunch of like insects that are all trying to get to like different locations that are all kind of jumbled together, like their traffic patterns are better. Like they can navigate optimally through this really crowded network. Yeah, kind of. Yeah, kind of.
Is there like a set month that you get your PhD?
It's not. I'm not making a lot of progress right now, to be honest with you. It doesn't. I'll be lucky to finish in the spring. Well, I mean, it was the more just having new classes, like the new class to teach, and then my daughter's here in the morning, so I lose all my morning time that I had to do stuff, and then have a new class that I have a lot more work to do than for a class I've taught for 10 years or whatever.
Do you like chocolate cake?
I'm a yellow cake guy. It's just vanilla. Yeah. Anyways, let's stop here. I don't think that this example, I still have examples left or whatever, but like they're just more examples that kind of doing the same thing over and over and over again here. If you guys want, we can certainly do some more examples from this section, but let's let you guys do some problems and get stuck and get frustrated and come back. Look, that's a normal part of the learning process. Like if you could do it perfectly the first time through, I would not have a job. You would not need me. And that's okay if you don't, but like most of us in mathematics try it once and we make a little bit of a mess out of it. You come back and get some more feedback, you try it again, it's a little bit easier, and you make a mess out of something else, and you come back and get a little bit more help, and it goes better again. And that's like the normal way it's supposed to work, especially when things start getting complicated and difficult and you're beyond just like, like if you have good instincts, everything is fine, math, right? Like if you have good algebra instincts, like up through like pre-calculus is pretty straightforward. You're not really nothing gets tremendously complicated. But here you have things that are just like instincts kind of fail us, right? Like to just figure out an optimization problem without having seen the process to do it, not at all obvious. Or it's like a related rates problem, or like, even some of the symbol pushing in these algebra things or the calculus problems can get really overwhelming. But anyways,